Our next speaker represents GE, and I think that's a particularly interesting company for us to listen to today, especially with some of our themes of kind of machine learning, Internet of Things, and artificial intelligence. And if you take a look at a diversified industrial like GE, they're very rapidly merging both the physical and the digital, and that'll have some interesting implications. And you'll see that across healthcare, transportation, power gen, jet aircraft, and more, or as Danielle likes to call them, hot spinning things. So central to this merger is a very robust R&D operation, because if you think about that diverse set of businesses, you can just imagine the diverse set of technologies, both digital and material science and chemistry, and increasingly biological, that you have to master to have this merger of the physical and digital. And so we're very fortunate to have the leader of the largest R&D center in GE's stable with about 1,500 scientists and affiliated techs, Danielle Merfeld. Danielle has a background in electrical engineering, both undergraduate and postgrad, understands the research enterprise very well as author and co-author of over 70 peer-reviewed papers. But what you might not know is that Danielle secretly aspires to perform the very first open heart surgery on the space station. So with that, please join me in welcoming Danielle Merfeld.
Every day, thousands of freight trains wind their way across countries around the world, hauling everything from grain and coal to automobiles and cargo containers. Shipping by rail is one of the most efficient ways of getting goods from here to there. And it's been that way for over 100 years. But the complexity of getting a train to its destination on time at the lowest cost has always been a challenge. Train length and weight, track conditions, grade, even differences between drivers can all play a big part in the speed and efficiency of freight delivery. And then there's the constant state of change. A sudden thunderstorm can add tons of extra weight to a mile-long string of open coal cars. In uneven terrain, the lead locomotive on that same train could be cruising down a steep incline while the cars in back are struggling to climb it. And in between, a powerful slinky effect of stress that can produce enough force to break the train in half. It's all about applying the exact amount of power at the exact time to control speed without using the brakes, harnessing the train's momentum to minimize the amount of fuel being burned while avoiding the destructive forces that can cause damage, and to do it while staying on pace for an on-time arrival. It's not easy. The precise application of power is critical to maintaining a perfect speed profile over a route that could stretch for hundreds of miles. 3 locomotives can generate nearly 13,000 horsepower, but on a train weighing 20,000 tons, that's like powering a full-sized car with the engine of a grass trimmer. You have to think very carefully about the hills and speed limits ahead, and you have to manage your momentum wisely. The smooth ride of a perfect trip can be almost impossible to achieve, even for the most experienced drivers. But the scientists at GE's Global Research Center have applied their brainpower to the challenge of giving freight trains a brain of their own. Trip Optimizer is an advanced system of software, sensors, and controls that uses technology to drive the limits of efficiency to new levels. It's like a smart cruise control for trains, expertly setting the best speed for each point along the route, looking ahead, analyzing a steady stream of data, and automatically making the right adjustments. Trip Optimizer starts by creating a mathematical model, a digital twin of the train and its trip, to predict the behavior of the locomotive and its cars along the way. It considers things like overall route, desired travel time, weight of the train, speed limits, changes in terrain. Trip Optimizer even reacts to changing conditions caused by the weather. Then, it calculates the best plan to complete the trip on time using the least amount of fuel and minimizing the coupling forces between cars. Leaving the yard, the system takes over and automatically drives the train according to the plan. Every tenth of a second, Trip Optimizer collects data from a complex network of computers and GPS systems, comparing real-time behavior against the digital twin model. If there's a variance between the two, things like speed, horsepower, weight, position on the track, the system sees it and reconfigures the twin to match, calculating a new best plan based on current conditions. Trip Optimizer is currently deployed on thousands of locomotives around the globe, including non-GE brands and models, and the results have been nothing short of amazing. In an industry where a 1% bump in efficiency can save 40 million gallons or more of fuel each year, in North America alone, Trip Optimizer is driving improvements up to 10%. Worldwide, that translates into billions of dollars in reduced fuel costs and hundreds of tons of emissions kept from entering the atmosphere. And it's just the beginning. Commercial aircraft models are being combined with route calculations to optimize the use of airspace, minimizing costly and annoying flight delays. And power plants are optimizing their output and revenues against maintenance needs and part life to be more profitable. It's all part of GE's mission to transform industries by connecting the physical and digital, sensing, predicting, and responding to make the world work better. And Trip Optimizer is one very good example of that mission in motion. All aboard.
So I thought that may be a fun way to really segue from a lot of the discussions we've been having so far that are based in the consumer world and the financial world to really heavy industry. And we'll talk more about Internet of Things throughout the rest of the day. So the idea of something that's a 100-year-old industry, you can see it's really not sexy. We try to make it look as sexy as possible in this video, but it's really not a sexy space. They don't really like to invest a lot of capital. It's certainly not where you'd imagine there to be a lot of high-tech computing power on board. But very interesting that you can change so much and you can increase the value of your assets so much with just a software change, just changing the behavior of your assets. So the idea of how do we harness this across industries requires a platform. This was one of our first big technologies that we deployed, really a digital technology in our industrial space. But developing that application, deploying it to all the locomotives, keeping up with all of the software updates, that's something that is going to be much easier to do as our platform emerges rather than these one-offs. We've heard about, GE's been talking a lot about our industrial internet vision, and I think the rest of the world talks about it maybe more in terms of Internet of Things, but really this feeds into that. We need the platform essentially to realize this vision. And I think maybe most simply put, the vision is taking digital technologies and applying them to the physical world, especially the industrial world, and extracting value, extracting productivity, whether it's cost productivity or other ways to look at value or performance. When we first started this journey, our CEO at the time, Jeff Immelt, really talked about this in a very similar way that we talk about the consumer internet. Very cloud-centric, tops-down, centrally managed. We even talked about it with respect to the power of 1%. So little tweaks, knowledge that we built in the cloud by extracting value across our fleets. 1% of fuel efficiency improvements for aviation could lead to over $30 billion of value over 15 years. 1% of fuel efficiency for a gas-fired power plant could lead to $66 billion. These big numbers with these little percents of improvement. What we've learned since then is that it's not just this tops-down, central focused, cloud-centric view, but in reality, much more of the value that we're going to create is from the edge of the industrial internet, at or near the asset. So let me start by just defining what I mean by edge. And I think many of you have already heard about this, but I just want to set a common platform for how I'm going to talk about it today. And the edge is really, very simply, the connection of the digital and the physical. It's where they really meet. So if you're at the edge, if you're an edge device and you're looking up at the cloud, you can access and see all the information technology, like big data, visualization, analytics. But you can also reach down into the physical assets that you're sitting on and access all the operational technology, like closed-loop controls, real-time security, machine connectivity. And at the edge, when you're doing computing, which, by the way, in the last 5 years, we have 100 times more performance at computing power at the edge. Computing at the edge means you're actually doing analytics. You're solving problems right at the asset where the data is being generated and where you want to use the information that you're creating in real-time access. So this is the big difference between what we thought when we started this process about a cloud-centric and what we're really doing with respect to the edge. But when you work at the edge, you're working in the physical world. And I want to really just geek out for a second and show you one very techie slide about what that means to be working in the physical world. Because when you are really controlling something physical, you have to remember that there are physical laws in play. Every physical thing has a natural frequency. So big things like a 60-meter-long turbine blade have a frequency a little less than a hertz. Small things like electronics or optical technologies, their frequencies are much higher. So their natural frequency might be 10,000 hertz. To observe that physical phenomenon, you have to sample twice within a cycle. To control that physical phenomenon, you have to sample 20 times within a cycle. So that means to control most of what we see, and this is just showcasing some of our GE industrial assets, you have to be able to sample and control within microseconds. Now, remember, think about the old version of how we thought about the industrial internet was very cloud-centric. There's no room in that loop to send information from a sensor to the cloud, perform some analytics and make a decision, send back the decision to then change an actuator, open a valve, move a turbine blade. There's just no time. So this has to be at the edge. So we're starting to see that physical limits, real substantial blocks, keep us from being able to operate in what is in the consumer industrial world the standard. Siri in the cloud, making decisions in the cloud. Everything can be in the cloud, not when you're doing industrial work. Most of the time, your physics keep you from being able to follow that same path. So one of the things that we did was actually in the last 7 months, my team at the Research Center developed what we're calling Edge OS. And it's very similar to iOS or Android OS. It's the operating system that sits at the edge, except for instead of sitting in your phone, it sits in your control system of your asset. Or in some cases, it's the gateway. It doesn't need a control system. But it's this software stack that's developed on a secure hypervisor. So that's the block along the bottom in the gray. And that allows it to talk to a real-time controls, which actually is the thing that is the see, think, do loop of managing that asset. But it's safely and securely connected to these cloud-sent applications that are containerized. So it's scalable. You can download a lot of different apps. It's software defined. Even the real-time controls is software defined. You can actually remake your controls. So your system can be improved without your system being changed physically. You can just change how you control it. You can change how it behaves. So this is really the piece that we added. We've had our Predix platform for several years. We've been talking about it. You've probably heard GE talk about our digital industrial future and our transformation and our Predix platform. Up until last year, it was very cloud-centric. So now we have really the cloud-to-edge platform built. And this missing piece that we just brought was this Edge OS. I want to showcase back to that example that was in the video, the trip optimizer. This is how it works in the platform now. So we still have all those digital twins. Those are the mathematical models, the representations of the train and the tracks and all the information that we have already based on our physics. But now that's built into this app, which is called Trip Optimizer, downloaded to the control system, which is on board the train. It's called GoLink. That just happens to be the name of the controls box. And it runs on the train. And now it's not the only thing that we're doing digitally with our diesel locomotives. We also have apps that run in the cloud. Those apps might manage the movement planner or yard planner, or two really great applications. Those are mostly fleet-based, not single train management. I'll show you one other example, which is very similar. You can see the platform at work has got a lot of common themes. This one is for a power plant. It's called Dispatch Optimizer. So you'll see the common themes here is that just like we had the digital twins of the locomotive, here we have a digital twin of the gas turbines, of the steam turbines. We even have twins of the most life-limiting parts of the gas turbine, like the coating on the stage 1 blade. And those are all part of the dispatch optimizer application that is real-time optimized. And the way that this works in a power plant is, now think about this as at the power plant level, not at the gas turbine level. So the power plant level now has this system controlling the whole plant as one entity. And it can look down into the system, into the plant, and say, okay, here's the life of my turbine, here's where I'm at, like an odometer view. But it can look up into the cloud and say, what's the price of electricity today? And on a hot summer day when the price of electricity is really high, it can make the decision to operate the system differently and actually overfire the gas turbine, consuming life much more quickly than it was planning for, but also making a huge profit because we're getting paid a lot for electricity that day. And on a different day, when the price of electricity is lower, it can underfire the gas turbine, conserving life, but it's a little bit inefficient, but overall keeping the outage date the same. No change in service productivity, no change from a plant manager view in terms of scheduling an outage, usually they're every 3 years. It's a big win. So by the end of that 3-year cycle, that plant would have made 3 to 4% more output. That can be a couple $1 million a year. No change in anything physical, no change in their service productivity, no change in the outage date, just running the plant differently. And what we found through this process was that it's not just the plant manager that we're going to talk to at a customer site, it's the energy trader of that same utility. So it's a completely different relationship now that we have with a customer buying our systems, and not just our gas turbines, but our digital solutions, because of what we're doing to impact that physical system. So I want to show you this sort of technical view of the cloud to edge, cloud to asset really view, because the Predix Edge, this Edge OS, is actually a really important link for our security aspect too. And security is really important here because as soon as you start saying to a plant manager or an aircraft engine provider, you're going to start hooking something up to the internet, that gets scary fast. So what we've done is we've put this unprecedented amount of checks and balances in place, and it starts with the hardware. It's that hypervisor, the bare metal of our Edge OS platform. So there's a thing called a Trusted Platform Module, TPM. It's actually a tiny little chip. It's rooted in the hardware. It's kind of our anchor at the edge. And that provides sort of like a fingerprint of trust. So you have, at every level of running this system, you've got it checking. So there's an authentication and certification, essentially checking the fingerprints against each other. For those of you who work for a big company like me, you probably see Safe Boot pop up on your computer when you're ramping it up, when you're booting it. This has effectively a check like a Safe Boot at the hardware level. There is a safe boot level. There's also a check at the hypervisor level. It checks again at the security level. It checks again at the communication level. And it checks again at the application level. So every level of the software stack that's running, every time it runs, gets authenticated and characterized as being safe. So that means we have to think about, there's any way that you could get in here and be nefarious with respect to a virus. This essentially will stop any software that isn't really authenticated to run from running. And that happens in the cloud. So this edge activity, the edge device and the edge stack, the Edge OS, is really this very important link for us in terms of providing security for this. I wanted to show the bigger ecosystem of the platform because there's a lot that's going on that's not in that edge piece. And it starts over on the left where we have an app development environment. So far, most of our apps are developed by our own engineers because they understand how the locomotive runs. They understand how a power plant runs, and they understand how a gas turbine life cycle operates. But that application environment, one of the things we did, and this is lucky for us because GE is such a big, broad company, to make it work across GE, it's almost as good as making it work across all industries because we cover a lot of them. So we made our app development environment able to ingest MATLAB code, C++, Go, you name it, we can ingest it because effectively we containerize it. So everything goes into a container, very much like a cloud operation, and then it gets certified. So the certification piece that happens in the cloud is also important. This is where the fingerprint gets applied. Public and private keys are used to authenticate. We, of course, have to have an app store. Just like an app store we're all familiar with on the consumer side, it's to expose our customers to our offerings and allow for a financial transaction to take place. And then the Edge Manager is an important aspect of the software deployment that sits in the cloud, and that effectively deploys the software and keeps up with any of the versioning control. And remember, you might download an app called Trip Optimizer to one train, but the next 2,000 trains also have an app. And they might all have a different tweak of that app, or they might have different versions of the app at different times, or have bought different features, and the edge manager is what keeps that all straight. So the last part is the edge device, which I've already talked about a little bit. That's the physical stack sitting at the edge. But this whole component, this whole ecosystem, no part of it works without all those pieces. So this is maybe how I would view the platform, but we haven't really talked about it as a platform. I'm learning so much through this process of being here today and just reading the literature in this space and understanding some of the ecosystem of a platform, because we think about this as just getting it out the door at scale. That's how we've been imagining this. I want to say one other thing, though, just because in reading a little bit more about this, it's nice to see that there are a lot of themes that are similar between the consumer world and what we're doing in the industrial world. And one point I thought was really interesting I want to share with you. I commented how security is one of the more important core design features of our platform. It also might be the most important application we are going to sell. And I want to walk you through one of this application in security called Digital Ghost, but let me give you the context first. So I'm going to use the power plant as just an example of a physical domain industrial application. Today, there's a lot of cyber threats and a lot of cyber concern, and there's already great protections in place. There's IT protections like antivirus software. There's OT protections like OpShield, or even just plain redundancy that keep bad things from happening. But what we've developed is a technology that's going to safe and keep what's not covered here safe and secure, and that is the sensors, the actuators, the control system. And the reason why we care about that is because back in 2010, many of you might remember the Stuxnet virus. This is a virus that was unleashed on an Iranian nuclear development program, and it essentially it overran its centrifuges and tore them apart, and it attacked the control system. So the way we think about this is, and the Digital Ghost application that we created actually uses the system that we understand to prevent that from happening. So if you think about a network of sensors, which a power plant has hundreds, if not thousands of sensors, no one of those sensors operates independently. Now, the way the Stuxnet virus worked is there was a sensor that effectively said, here's the rotation of the centrifuge. And the control system looked at that and said, well, that's not fast enough. I better speed it up. And the sensor would say, here's the new speed. Oh, that's not fast enough. I better speed it up. In actuality, it was going pretty fast. The sensor was being spoofed. And so the control system kept speeding it up and speeding it up and speeding it up until it broke. Now, this took over 2 years. This virus was at work and a typical control system virus attack is over 200 days before it's found. It's in the system for over 200 days on average, which is so scary to think about. But with this approach, what we're doing is we networked all the sensors. So for example, in a power plant, if a sensor were saying, oh, your firing temperature isn't high enough, and the control system would normally turn up the temperature, before that happens, there's another sensor downstream that measures the exhaust, or the NOx emission, or the data, or the output. And it can look at that and say, well, wait a sec. Your sensor doesn't seem to be right, because down here, we're seeing what the data should look like if it were hot enough. So now the system can say, aha, something's wrong. And maybe there's not one, maybe there's a dozen sensors that have been spoofed. So we can look and say which sensors are real, which sensors are being attacked. And so we can identify that we're under attack, and it's not going to take 200 days, it's going to happen in seconds. Then we can localize which sensors are under attack. And then we can even use the sensors that are still okay to provide virtual dynamic sensors that are in the place of the sensors that we're going to take offline. So without even a human in the loop, we're now able to detect, locate, and neutralize, effectively creating an immune system in our industrial assets. In fact, one of the scientists on the team who developed this had actually worked in human biology immune activity before. So him coming in and us thinking about how to create these protections was almost too good to be true. So that's the great thing about working in a research center that has all these different technologies coming together. You will have somebody who has experience in human biology working on industrial security. Just to start to wrap things up, I thought I would showcase some of the things we are thinking about now that we're talking about it as a platform, and some of the fundamentals. I won't go into a lot of details because I've talked about how we made it scalable and why it matters that it's safe. But ease of use, it sounds trivial, but as much as we can make this so easy that our customers can't imagine not using it, for example, plug and play, to set up a power plant, to put in an aircraft engine, to set up a electrical yard, those things take time. If we can make it plug and play, which means the sensors talk to each other, everything self-identifies, you plug it in and it knows what it is inherently, we can save 50% of our commissioning time, which for a power plant could be months. We can save 30% of our engineering requisition costs and time. These are big, big numbers when it comes to these industrial costs. At the bottom half, the core interactions, this is where we start to think about not just how we developed a platform, but who's going to use it and who's going to consume it, who's going to make applications for it, and how do we expect it to be used. And I want to jump to one application about learning-enabled asset behavior with this just one example. What you see on the left is a tops-down view of a Doppler map of a wind farm. This is actually a corner of a pretty large wind turbine. It's a small corner of a large wind turbine, wind farm in Illinois. And the black dots are the turbines, and those blue streaks are the wake of the wind, so the lower speed, because the turbine has now absorbed a lot of the power out of that wind. So behind the wind turbine, it's lower speed wind. Typically, when our wind farms are first being developed, we optimize every turbine to be out there, sort of every turbine for itself. So every wind turbine was optimized to take as much wind as it could grab. But what we understood is that if they work more like a flock rather than a collection of individuals, when one turbine has 2 or 3 in its wake, they can talk to each other, and that turbine can say, oh, well, let me just pivot my blades a little bit, or maybe I'll yaw and put my wake over to the side, because then the 2 or 3 behind it can capture more wind, even though the one in front is a little less efficient, and overall, the wind farm makes more power. We've demonstrated in several places with very just quick algorithmic input, 1% more power, which sounds pretty good, not that great, but that's 4% more profit. So what we want to do is to be able to create a learning-enabled asset where these wind turbines can now talk to each other and learn how to make more overall power without a human in the loop, without us injecting another algorithm. They can look and experiment and try different things, even share their own health. Or when one turbine goes offline, the other turbines understand what that means in terms of what total power can be put out. So we can unlock this value across industries. Now, just as I mentioned in the beginning, that we didn't really know as much about how important the edge would be when we first started. We thought more cloud-centric. There's still a lot of things that we're learning, and a lot of decisions that we have yet to make as we fully develop and exploit this platform across just the industries that GE is in. One of them is how open or closed will this platform be? We're developing it primarily with the GE industries in mind, but we understand that it's going to be more valuable when it's adopted more broadly. Our API is already open, but is it just our customers and our own engineers that will use it? Can we bring in third parties? App development environment. Are we going to train people? This is a great thought that came up just in preparing for this talk. How are we getting more people on our application development platform? And whether or not this is common across many industries or whether it's just in the industries that we are thinking of for GE, how do we make sure that we keep it open enough that we can exploit new technologies? Artificial intelligence, machine learning. As those change, this has to be modular and evolutionary enough to absorb that and be able to grow and adapt as we go forward. So I thought I would just lay out the big picture of industrial platforms, and specifically how cloud, edge, and application all flow in together. And we have enough time, I think, for me to take a few questions. Thanks.
Started here. Hi, I'm Joe Byron from PTC.
Yeah.
So I know Predix pretty well, and also as a technologist, I typically think of technology platforms, and the Platform Revolution book, which there's a bunch of copies on the table outside, by the way, really opened my eyes personally to the idea of the economic platform. Sounds like you're starting to noodle on that as well. What are your sort of instinctive notions of, to use the terminology of that book, the value units that you would see exchanged? You know, for example, you talked about applications. Could you also see digital twins exchanged in a marketplace, or exchange of data for the purposes of third parties building digital twins and feeding them back into the marketplace?
Yeah, those are great questions, and I would say the most, the initial approach, which I would admit is probably the basic, maybe I wouldn't say naive because this is being recorded, but the most basic way to think about the value system is as we're creating a bunch of value, as we're creating millions of dollars more profit for a plant, how much of that is shared between the developer, the app developer and the user of that system. I mean, if you already own the power plant, you feel like it's all yours. If you're the one who wrote the app that extracts all that new value, you feel like it should be all yours. How do you divide the value? So that's one value unit. The other piece, though, you mentioned, which was quite interesting, is the digital twin. Most of these applications are based on the physics of the system, and the physics of the system is wrapped up in a model called a digital twin, which are really it's not really just a model, it's much more than that. But when you develop a digital twin of a wind turbine, you can use it in 100 different ways to do 100 different things with that wind turbine. That has value. So do you just put it in your app and walk away? Do you maybe have to make 100 apps? Do you sell it to a bunch of other people for them to make apps? That is completely open. The sky's the limit when it comes to how we monetize that. And frankly, I think just getting to the point where we're thinking of our GE digital business as a vertical business and not just as a horizontal support for our industrial businesses, we're starting to make those moves to be more independent, thinking about the digital value versus the industrial service value. Thank you.
Thank you. Thank you, Danielle.